aside from the basic integration by parts formula, there's a few kind of standard techniques or standard applications of this integration by parts technique. So we'll look at those in these examples. Before we get started on that, though, I wanted to introduce you to, so we're doing integration by parts, and let's get on the right layer, and this acronym, LIATE. This acronym has to do with choosing U, because you've got to choose your U and your dV, right? And this goes from the best choice through to the worst choice for U. And this is based on the type of function. So L is a log function. That's the best choice for U. Then an inverse trig function is the next best choice for U. Then an algebraic function, like x squared or something. And then trig. And exponential is about the worst choice for U. Typically. And this is kind of a rule of thumb, but generally tends to be true. So let's take a look at this problem over here, integrating x squared e to the x dx. So you look at that, you've got to pick something to be u and something to be dv. And we know about the worst choice for u is to be an exponential. So let's let x squared be the u. And let's let the exponential and the dx be dv. So before we get started on this, let's set up our u and our dv. So u is x squared, dv is e to the x dx. I gotta get rid of this thing. Okay. Du then would have to be 2x dx. And v would be the integral of e to the x. And fortunately, integrating e to the x is easy. It's just e to the x. So now we are ready to set this up. And we'd say our integral is equal to ultraviolet voodoo. So ultraviolet, there's ultraviolet minus integral of voodoo. Du is 2x dx. And like always, we hope that the integral over here is easier than the one we started with. And it is. But if you look at it, you'll notice it needs integration by parts again. Oops, x squared. Okay. So I'm going to move the 2 out front, but I'm going to say basically we've got x e to the x dx. Pretty similar to what we started with, actually. It's just one lower power of x. And when we lower the power of x by repeating this process one more time, then we'll be done. So this is going to require 2 integration by parts. So for this piece over here, I'm going to choose u to be x and dv to be e to the x dx. Means du is 1. Derivative of x is 1. And v is e to the x. So let's keep going on our integration here. I'm just going to copy down the parts. Keep forgetting that x squared. Copy down the parts we already have. Okay. So now I'm working on the integral. And this integral, I'm going to use integration by parts. So it's ultraviolet. So x e to the x minus the integral of voodoo. So v du is just dx. And thankfully, this integral now is easy to do and does not require integration by parts. So let me rewrite this one more time and we'll be done. X squared e to the x. I'm going to go ahead and distribute this minus 2. Notice it distributes here and it also distributes here. So I've got minus 2x e to the x and minus 2 integral of e to the x, which is just e to the x. Now this is an indefinite integral, so don't forget a plus c on the end. And we are done. Technically, you got a plus c every time you did an integral. So we actually had 2 different plus c's. But when you add an arbitrary constant to another arbitrary constant, you get yet a third arbitrary constant. So it's typical just to wait until the end and just stack one arbitrary constant on the end. Okay, so that's the idea of sort of using integration by parts multiple times. Let's do another example. This is integral of natural log of x dx. It seems like it should be a basic integration formula, but it's one we don't know yet. It's also one that doesn't really seem like it's a good candidate for integration by parts, because it doesn't really have 2 parts. Or does it? You can always make anything into let's get on the right layer again. You can make anything into a multiplication by just putting a 1 in there. So let me pick my parts. Using LIATE log functions are pretty much your best choice for u. So let's go u is natural log of x, and that makes dv just 1 times dx. So the derivative of u, du, is 1 over x dx. The integral of 1 is just x. So let's work out our integral here. So it's ultraviolet, so x times natural log of x. I'm putting that in VU form, but it's u times v. Minus the integral of v du. V is x, du is 1 over x. That's actually going to work out nice. So x natural log of x minus, this simplifies to the integral of 1 dx. So x natural log of x minus x plus c. And some people do actually memorize this because it is the integral of one of our basic functions. It's the integral of natural log of x. And the integral of natural log of x is just x natural log of x minus x plus c. I personally don't memorize that as a formula. I kind of just run through the integration by parts every time because I don't like memorizing. But it's totally up to you if you want to memorize that or just be able to do that, one or the other. Okay, so let's look at our last application of integration by parts here, which is e to the 2x times sine x dx. Seems classic for an integration by parts problem. And if we follow LIATE, I would say exponentials are the worst choice, and trig functions are the second worst. So let's go with our u being our second worst option rather than our worst. So u is sine of x, and dv is e to the 2x dx. That makes du cosine x, and it makes v. Integrating e to the 2x actually requires a tiny little u substitution. U would be 2x, and I'm not going to run through that, but it ends up, we've done that before, it ends up being 1/2 e to the 2x. And this is a little worrisome because I think you can already see when we write the integration out, the new integral is not necessarily going to be easier than the old one. But let's go ahead and try it. So it's ultraviolet, so UV, And I'm going to move the 1/2 out front. Let's go 1/2 sine x e to the 2x. So there's uv minus v du. And I'll pull the 1/2 out front of that. And there's v du. And notice that our new integral here looks like it needs integration by parts. So we could do integration by parts again. But notice too what's happening here is I've got e to the 2x and cosine x. I've got an integral that is no simpler than the one I started with. And you feel like if you're going to do integration by parts again, I'm going to get something that looks a lot like what we just started with. And that's actually going to be a good thing. So let's try it. Let's do one more round of integration by parts. I'm going to recopy, maybe I'll move the e to the 2x out front. Okay, let's recopy. And let's do integration by parts again. Let me choose a different color here this time. I'm still going to make my u the trig function, so u will be cosine of x. And dv will be e to the 2x again. And I'll get my du, which is negative sine. And I'll get my v, which is 1/2 e to the 2x again. Okay, so I'm ready to do integration by parts again inside here. So we'll do ultraviolet. So let's see, I'll move the 1/2 out front. Actually, we'll move the 1/2 e to the 2x out front, cosine x. There's my ultraviolet. Minus voodoo. And I'll move that 1/2 out front. And I've got e to the 2x. And I've got negative sine x, so let me turn that into a plus sine x. So yeah, this looks like it's not getting any better. It looks like I could just keep doing this forever. But let me rewrite the whole thing from the very top. So I started with integrating e to the 2x sine x. And so far, what I know is that's equal to 1/2 e to the 2x sine x minus, and I guess I'll go ahead and distribute this 1/2. So minus 1/4 e to the 2x cosine x. And so far that's great. There's no integral stuff, but the last bit's going to be an integral. Let me distribute that. So it's going to be minus 1/4 integral e to the 2x sine x, and I forgot the dx on the end up here. And you're like, great, I just got back to where I started, more or less. And like I said a second ago, that's actually going to be a good thing. Now notice what we've got right here is the exact same integral as what we started with. Granted, there's this minus 1/4 out front. But that means I can finish solving this equation, not with calculus. I can finish solving it algebraically. I'm actually going to treat this like a term, which it is. I'm just going to add 1/4 of e to the 2x sine x dx to both sides of this equation. And this is going to allow us to actually finish this problem. We're going to have 1 of this integral plus 1/4 of this integral. So add 1 of something to a 1/4 of something, you get 5/4 of that thing. So 5/4 integral e to the 2x sine x dx equals this stuff right here. Which I'm just going to be lazy and drop down into there. And I'm technically still one step away from done because I need to solve for the integral. So divide both sides by 5/4 or multiply by 4/5. Maybe that's a better way to say it. So it equals 4/5 times 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. I could distribute that 4/5, and the ultra important part, don't forget a plus c. And finally, we've sort of taken this circular path, started with a lot of hefty calculus and ended with some algebra, and we're able to algebraically solve for the integral. Now this is a specialized technique, this last problem, that really only works when the derivatives and integrals keep repeating themselves, which really only happens with trig functions and exponential functions. So if you have a trig times an exponential, usually you can do integration by parts twice and then get this algebraic ability to solve for the integral. All right, that's enough. I think you are ready to tackle integration by parts.